Hello everyone, this is Shudhanshu Sarkar, Assistant Professor, Department of Electrical Engineering, Narula Institute of Technology. So today the subject is electrical circuit and network, and from this subject I will talk about the J operator. So today's topic is J operator, main topic. So this subject I have to cover total 3 module, unit 2, 3 and 4. In unit 2 we have single phase AC circuit and resonances. Then in unit 3, principle of circuit analysis, AC and DC circuit. This part is already covered. And then in unit 4, that is the networks theorem, statement, procedure, areas of application and limitations. So today I'm going to talk about the study of J operator and some concept of complex impedance, rectangular and polar form. So single phase AC circuit and resonance is the chapter name. So today's main topic of discussion is study of J operator, concept of complex impedance, rectangular and in polar form. So now let me start about what is J operator. I think all of you are well aware of the J operator because this topic is already covered in your mathematics syllabus, that what is J. The J operator comes from the complex numbers and states that J equals to root over minus 1. So I think this is very common to all of you that the value of J equals to root over minus 1. So you have to remember this way, that the value of J equals to root over minus 1. Now tell me what will be the value of J square. It is very easy to say that the value of J square is what is the value? What will be the value of J square? Tell me. You can answer. Nothing but root over minus 1 whole square. The square and root will vanish. The value will be minus 1. Okay. So this J operator will help us in different way to solve the complex circuit, to solve AC circuits. In terms of circuit theory, we will interpret the symbol J. We interpret the symbol J when placed in front of a phasor to mean advance the phase of the phasor by 90 degrees. Okay, so it's actually advances the phase of the phasor by 90 degree, and minus J means, so what will be the meaning of minus J? Retard the phase by 90 degrees. So remember this part and try to understand this one very carefully, that this is actually the application of J in circuit theory analysis. So symbol J when placed in front of a phasor. So if we place J in front of a phasor, then what will happen? To mean advance the phasor of a phasor by 90 degrees, and minus J to mean retard the phasor by 90 degrees. So minus J, if we put it in the phasor, so retard the phasor by 90 degree, and if we plus J means advance the phasor phase of the phasor by 90 degree. So this is one of the significance of J operator. Thus, we can say that J into V0 sine omega 0 t. That means we can write in this way that advance the phasor 90 degrees. So what will happen? So it will convert to V0 cos omega 0 t. And if we multiply J with V0 cos omega 0 t, then what will happen? Minus V0 sin omega 0 t. So this angle is rotating with the multiplication of this J. Now we can now redefine impedance as a complex quantity, although sometimes it may be purely real or purely imaginary. Try to understand the words, the meaning of the word, the meaning of all the words which are written here in this lecture. We can now redefine impedance as a complex quantity, although sometimes it may be purely real or purely imaginary. So for a resistor, ZR equals to Z, a real quantity. So what is this? For a resistor, ZR equals to Z for a real quantity. So for inductor, what will happen? ZL equals to omega J omega L, that is imaginary. And for capacitor, we also know that Zc equals to 1 by J omega C, that is also imaginary part. So sometimes it may be purely real or purely imaginary. Is it clear to all? When it is ZR, then it is only Z. So we know that Z is a complex quantity because Z is the summation of R plus Jx. Sometimes it is R plus Jxl, or sometimes it is R plus Jxc, or the difference between XL and XC. So for resistor, it is positive real quantity. For inductor, it is imaginary quantity, and for capacitor, it is also imaginary quantity. This is very important to understand. That how we can define this complex quantity. So please remember like this. Sometimes it may be purely real or purely imaginary. For resistor, it is purely real, and for inductor and capacitor, it is purely imaginary. So this is the important part. Here, the modulus of complex Z gives us the correct amplitude relation between V and I, and its argument gives us the phasor relation. Look, so if Z is a complex quantity, we know that complex Z gives us the correct amplitude relation between V and I, and its argument gives us the phase relation. So what is the significance of Z? It gives us correct amplitude relation between V and I. Okay, amplitude relation between V and I, and its argument. So what is the purpose of its argument? Gives us the phasor relation. This is the most important part to remember from here. Now, if we consider V equals to IZ, we all know that as per Ohm's law, it is V equals to IR. But for AC circuit, we can consider V equals to IZ. So when it is V equals to IZ, so it works every time and gives us the phasor information. So when it works every time, and it gives us the phasor information. This is one of the very most important short type question, that what is the significance of V equals to IZ. So you have to answer like this. It works every time and it gives the phase information. Next, if we drive a current I0 sine omega 0 t through an inductor, the resulting voltage will be VL equals to j omega 0 L I0 sin omega 0 t. And we already defined this part in the previous slide, that if we multiply j with this term, then what will happen? So it will convert to sine to cos, because with the advancing, the phasor will advance. So omega 0 L I0 cos omega 0 t. So this j is actually changing sin omega 0 t to cos omega 0 t. Now, or through a capacitor. So the last one was, if we derive a current I0 sin omega through an inductor, so if the current through a capacitor, then what will happen? Vc equals to 1 by j omega 0 L to a capacitor omega 0 c. This should be c. Just this part, this will be c. One by j omega 0 c I0 sin omega 0 t. That means the current, the AC current is flowing through a conductor. Then what will happen? Minus 1 by omega 0 c into I0 cos omega 0 t. So sin omega 0 is converting to cos omega 0 c. 1 by j is minus 1. So actually rotating, the phase is advancing for this case also. Now, if you consider this simple circuit, so here in this circuit, what can you find? Here we have a supply voltage Vi and a voltage at the load, and that is V0. The resistance which is connected. So what I'm saying, just let me show this. Vi current. This is the resistance. This is the inductor. This is V0. The impedance of these combinations is circuit diagram as Z equals to R plus J omega L. This is the impedance of this combination, because only the inductor is connected. So we will now use V equals to IZ. Hence, what will happen? V0 equals to, now if we use this this one, V equals to IZ, then Vi will be equals to I into Zi. If Zi is, we already know Zi equals to this part J omega L, and Vi equals to I Zi, and V0 will be equals to I Z0. Where Zi, what is Zi? In the last slide, we already talked about this. Zi equals to R plus J omega L. Zi equals to R plus J omega L, and Z0 equals to J omega L. So Z0 value nothing but J omega L. The ratio of current to the voltage is given by the modulus of Zi. Look, this is very, the ratio of the current to the voltage given by the modulus of Zi. That means Z equals to V by I. So Zi will be equals to root over, what will be the value of Zi? Root over R square plus omega L whole square. Modulus of Zi is root over R square plus omega L whole square, and the phase angle between them is given by the argument Zi, argument of Zi. So that is, we already know it from class 9, that will be equals to tan inverse omega L divided by R. So this is the argument, tan inverse omega L by R. Now convert complex number from rectangular form to the polar form. So how can we convert the complex number from rectangular to polar? I'm going to discuss on this. For that, first try to consider axis. This is x-axis. This one is y-axis. Consider a point here, that is z. So the distance of this point, or you can say the point is P. The distance of this point from the base, the distance is y. So if we consider the point is x, comma y. So from here it is y, and from here it is x. This is y distance. This one is y. This one is x. Now this is y. This is x. So xy point. So as per the rectangular form, you can say z equals to x plus iy. And we consider the angle is theta, and the distance from the center to that particular point is r. The angle is theta. Now r equals to z. If we consider this is z, so what will be the value of z? Or you can say the r should be equals to mod of z. From coordinate geometry, we know this concept, that is equals to, this is x square plus y square. So r equals to mod z, that is equals to root over x square plus y square. And if, with the help of the coordinate geometry or trigonometry, you can easily calculate that x equals to r cos theta, x equals to r cos theta. X equals to r cos theta and y equals to r sin theta. Because we know that cos theta equals to x by r, that is base divided by hypotenuse. And sin theta, we know that sin theta equals to y by r, that is the height divided by r. So y equals to r sin theta. Now what will be the polar form of this? This is the polar form. So z, we can write z equals to r cos theta plus I sin theta, because we already explained this is the rectangular form, x plus jy. So what is x? X is r cos theta. What is y? Y is r sin theta. So r into, the value is r, we take common r cos theta plus this I. This is the I sin theta. Let me show you I. So where is I? This is our I. This is the I. Okay. So z equals to r into cos theta plus I sin theta. So in this way, we can convert rectangular form to polar form. Now, phasor polar form, I already explained this in the previous slide. Let me show you in this way also. Phasor polar form, v equals to v angle, v equals to v angle, v vector equals to v angle theta. So what is A? I already told you that what is A equals to v cos theta, v cos theta. This was R for the last diagram. And what is B? Is v sin theta. So here this circuit diagram, you can find a Z. that is L plus R, the combination of L and R. So what is Z? We know that Z is R plus JXL. R here it is obviously RL plus JXL. Now, if we consider a value, if we want to convert it from, this is the normal trigonometry. If the value is xy, the point is xy, the distance is r, and the angle is theta, so r equals to root over x square plus y square, theta equals to tan inverse y by x equals to r cos theta, already told in the last slide, x equals to r cos theta, y equals to r sin theta. And in mathematical way, if you want to uh, convert it from rectangular to polar, then you can define like in the value, this point, previously for trigonometry it was xy, for here it is r and xl, inductive reactance. If the angle is theta and if the distance from the center to that particular point is z, so z mod equals to root over x square plus r square plus xl square. This is r phasor, xl phasor. Now theta equals to tan inverse xl by r, and r equals to, what will be the value of r? This is r. So r equals to z cos theta and x equals to z sin theta. So in this way we can conclude this chapter. In the next slide, I will discuss more about the topic in the easiest way. I will try to show you inductance, capacitance like this. So these are the references I used to prepare this PowerPoint presentation. And now I thank you everyone for watching this video. For any doubt, you can mail me or you can contact with me anytime. Thank you all.